Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're looking at the 2025 exam paper and specifically question 4. So we're going to be looking at a little bit of collisions here, but it's going to be mostly some vertical circular motion. So two smooth spheres, A of mass 2 kg and B of mass 1 kg, are attached to pegs of equal height by two light inextensible strings, each of length 30 centimeters. The spheres are initially at rest. A is released when the string is taut and horizontal. A collides with B, which is suspended vertically. So we can see this in our diagram. The coefficient of restitution between the spheres is 3 over 50. Show that A strikes B with speed 7 root 3 over 5 meters per second. So what we have here is A moving from one position to another and swinging in this vertical circle or part of a vertical circle. Where we have this swinging, we're always thinking about our principal conservation of energy. So here's position 1 and here's position 2. So if we think about our conservation of energy, the kinetic and potential energy combined at position 1 will be equal to the kinetic and potential energy at position 2 just before it hits B. So this is what it breaks down to: a half mu squared plus mgh1. So the height of position 1 should be equal to a half mv squared plus mgh2. So at position 1, our sphere A is released from rest. So U is equal to 0 meters per second. And the height, because of the way it's held, is just the length of the string, which is 30 centimeters, or if we want to work in meters, which is better, 0.3 meters. So then at position 2, we don't know V. That's actually what we're trying to work out. But we do know its height, and that's going to be 0 because it's at its lowest position. Our height is always compared to our lowest position. So now we just need to fill all this information in. So we have a half, our mass of A is 2, our U is 0 squared, plus 2 times G, which is 9.8, times H1, which is 0.3, and that is equal to a half. Instead of M, we're putting in 2, V squared plus M G times 0. Okay, so that's gone and this bit's gone. So to get and a half times 2 is just 1. So V squared is equal to 2 times 9.8 by 0.3. And that works out to be 5.88. And then V is going to be the square root of 5.88. And when you put that into the calculator, we should see that that answer is the same as 7 root 3 over 5, as they asked. It's meters per second. So part 2 asks us to calculate the speed of each sphere immediately after the collision. So let's set this up as we would for any impact. So the way that they hit it is a direct impact. So we have the sphere A before the collision is that 7 root 3 over 5, which we have just worked out. Its mass is 2, and we don't know this. Let's call this one x. For B, it starts at rest. It has 1, and let's call that y. So we have two things that we need to do anytime we're working with collision. So Newton's law of restitution. So that's going to give me x minus y is equal to minus e, so that's minus 3 over 50. And then that's 7 root 3 over 5 minus 0. So this effectively gives us x minus y is equal to minus 21 root 3 over 250. And then the second thing we do is the principal conservation of momentum. So that gives us 7 root 3 over 5 times 2 plus 0 times 1 is equal to 2 times x and 1 times y. And that's going to give us 2x plus y is equal to 14 root 3 over 5. So putting those two equations together, let's solve them simultaneously. So we get x minus y equals minus 21 root 3 over 250. X plus y equals 14 root 3 over 5. And then, oh, sorry, that should be a 2x here. So we get 3x equals, oh, it's going to give us 2037 root 3 all over, sorry, I've crossed this out by accident, root 3 all over 750. Divide that by our 3 and we're getting 679 root 3 all over 750, or in decimal, that's going to be 1.57 meters per second. So that might be easier to work with. So then we have y is going to be equal to x plus 21 root 3 over 250. So let's put that back in. Y is equal to 679 root 3 all over 750 plus 21 root 3 all over 250. Again, you can work in decimals. There's absolutely no issue. And this is 742 root 3 over 750. And that is 1.71 meters per second. So the particle A afterwards, 1.57 meters per second, and B, 1.71 meters per second. Do note that they've said speed. Now, both of ours are positive, so it's not an issue, but that's something to watch out for in other questions. So part 3, show in a diagram the forces acting on B when the string makes an angle of theta with the downward vertical. So here is our particle and we have the weight acting down. And then here is the tension in the string. And our acceleration, because this is circular motion, our acceleration is towards the center of the circle. So that's a really helpful little piece of information for us as we move on with the question. It is enough to simply have the tension and the weight on your diagram, but that acceleration will help you as you move forward. So I'm also going to do some resolving. Again, we don't need resolving for part 3. So to get our marks in part 3, we don't need it. But resolving is going to make it a little bit easier for us as we move forward. So remember, we want to have all of our forces parallel or perpendicular to the acceleration. So for us, that means that tension is fine because it's parallel to our acceleration, but weight needs to be resolved. So let's do this parallel and perpendicular to A, which are these two bits here. Here is our angle theta against the downward vertical, making this mg cos theta and this mg sine theta. Part 4 then asks us to write an expression in terms of theta for the height B has moved through when the string makes an angle theta with the downward vertical. So what we want to do is understand what has happened here. So let's go back to our original diagram. So by the time B has moved into this position, what we effectively have is we can make a little triangle to figure out this height here. So here's position 1 and here's position 2, and I'm going to connect position 2 back to the original position 1. And you can see here we've made a lovely little right angle triangle. And based on that right angle triangle, we know that the length of the string here is 0.3 meters. And then from kind of a bit of calculus, for a bit of trigonometry, we can say that this is 0.3 cos theta because it is the adjacent side. So we have this little portion of that string. Now remember, it is still the string. So to get this missing height, we have the length of the string, which is 0.3, and then we take away the bit that we've calculated in our triangle. So effectively, our expression for our height is simply 0.3 minus 0.3 cos theta. So part 5, write an expression in terms of theta for the speed of B when the string makes an angle of theta with the downward vertical. So first we're going to start with the conservation of energy because we're dealing with the vertical circle. So we're going to use this to find B. So our kinetic energy plus potential energy at position 1 is equal to the kinetic energy plus potential energy at position 2. Position 1, remember, is when B is hanging vertically down, and then position 2 is when it's an angle theta to the horizontal, or sorry, to the vertical, theta to the downward vertical. So this breaks down to a half mu squared plus mgh1 is equal to half mv squared plus mgh2. So the initial speed, we've already worked that out from our collision. That's our u. Our h1 is going to be our 0 because it's at the bottom. V squared is what we're looking for. And then our height, our h, when it makes an angle theta, we've already worked that out in part 4. So this is what it works out as. Because we know b is 1, we can put in m as 1, but actually m is just going to cross itself off here. We can divide across by that. It's not going to have any impact at all. So mg times 0 is going to disappear as well. So what we are going to get here when we rearrange, so first thing we'll do is let's multiply across by 2 to get rid of those halves. That's going to give us a 2g 0.3 minus 0.3 cos theta. So v squared is equal to that initial speed, which I've written in third form, 742 root 3 over 750, all that to be squared. If you use the decimal form, we're going to work out pretty much the same answer. Minus 2g, 0.3 minus 0.3 cos theta. So now that I have v squared, we can go the step further and get v, but because remember for vertical circular motion, we don't usually find our v, but here in this question, they asked us specifically for the speed. So it depends what way a question is worded. Here, because we want the speed, we're going to stop at this point. If it's just a full circular motion question where we're working through to something else, so like in this case, the value of theta, we'd stop at v squared. But be aware of that v squared there because we can plug that in to make life easier for ourselves. So we're told that find the value of theta such that the string B has a tension of 15 newtons. So just bringing back our diagram we've had, so here's our resolved piece. So we need to think, so after you've done the conservation of energy, the next thing we always think about is what is the centripetal force? So what force is acting as a centripetal force and which formula should we use and why? So look at where our acceleration is going. Okay, so let me highlight it so we can, here. So here's our acceleration pointing that direction. So any forces along this line are going to act as a centripetal force. So we're going to have a tension, which is helping it, and then this mg cos theta, which is going the opposite way, and that's going to be a minus. So, and then we need to think about our formula. So which of these two are we going to use and why? So, okay, so our centripetal force, so Fc, is going to be our tension minus mg cos theta. And we're always looking at using the formula with v squared when we're dealing with vertical circular motion because we're always working with the conservation of energy. So we're never dealing with omega in that case. So we know that T minus mg cos theta is equal to mv squared over r. So we also know that T is 15, and we're going to sub all this in. So T, which is 15, minus mg cos theta is equal to m. I've put in that v squared from above, so v to be squared all over our r, which is 0.3. That's the length of our string. And now all we need to do is work this through. So remember our mass for this is 1 kg, so we can sub that in. And it leaves us here with 15 minus 9.8 cos theta is equal to 5.88 cos theta minus 2.944. And then I brought that 0.3 across the equals. That then multiplied out gives us this. Let's get all our causes on one side, numbers on the other. Let's divide so that cos theta is on its own. That gives us 0.844. And then cos inverse gets us to our 32.4 degrees. So we're following the same steps as any vertical circular motion question, but it's just been broken down into these two parts.